I am Vivek Bajpai. Now I am starting class 10 CBSE board maths irrational number exercise number 1D. Every non-terminating and non-repeating decimal is irrational. Please like, subscribe, share my channel and watch also, and give the comments of your. I will welcome it. Thank you. I will start. The irrational numbers are the numbers which are non-repeating, non-terminating, non-repeating. Means the number is not completely divisible in any case. But also it is the numbers which are coming on are non-repeating. Just like you can see that 10, 100, 1000, and then after 10,000, 1 lakh, means nothing is repeating. Same to that you will see it. And the other type which you studied in a previous classes also, that root 2, root 3, root 5, root 6, root 7, root 10. Third type, it is the cube roots of the numbers. Cube root of 2, cube root of 3, cube root of 5, cube root of 6. And the fourth type, pi is an irrational number while 22 upon 7 is rational number. Let P be a prime number and A be a positive integer. If P divides A square, it shows also if it divides P square, P also divides A. Proof: let P be the prime number and A be a positive integer such that P divides A square. We know that every positive integer can be expressed as the product of primes. Let A equals to P1, P2 and Pn, where P1, P2 to P1, P2 to Pn are prime. Not necessarily all the distinct. They are not distinct. They are same. Then A square is equal to P1 plus P2 plus Pn. Again P1 plus P1 comma P2 to Pn. A square means P1 square, P2 square to Pn square. Now P divides A square. P is a prime factor of A square. P is one of the P1 to Pn. P divides A. Thus, P divide A square also. So, P divide A. If P is a prime number, then prove root 2 is irrational number. Let P be a prime number and if possible, let root P be a rational number. Let P be the prime number, if possible, let root P be a rational number and let its simplest form be root P equals to m upon e. That is letting. That we let, where m and n are integers having no common factor other than 1 and n is not equal to 0, because we know that rational numbers have a denominator 0. Then root p is equal to m upon n. On squaring, p root p square is equal to m upon n whole square. P is equal to m square upon n square. Then m square is equal to pn square. P divides m square, P divides m. Let m equals to pq for some integer q. Putting m is equal to pq, in first we get pn square is equal to p square q square. Both sides have p common, so that we Cancel p and in p square also p. Then it's left n square is equal to pq square. P divides n square. It also divides n. Thus p is a common factor of m and n. But this contradicts the fact that m and n have no common factor. Only one is a common factor. But the contradiction arises by assuming that root p is irrational. Hence root p is irrational. Example number 2, prove that root 2 is an irrational number. If possible, let root 2 be the rational and let its simplest form be a upon b. Then a and b are integers having no common factor other than 1, and b is never b equals to 0. Now root 2 equals to a upon b. On squaring, root 2 square a upon b square, it is 2 is equal to a square upon b square, so that a square is equal to 2b square. It is equation number 1. 2 divides a square by this, then also 2 divides a. Let again be a is equal to 2c for some integer c. Putting this a is equal to 2c in equation number 1, we get 2b square is equal to 4c square. B square is equal to, we take out the two common numbers. Then 2 divides b square, 2 divides also b. Thus 2 is a common factor of a and b. But this contradicts the fact that a and b have no common factor other than 1. The contradiction arises by assuming that root 2 is a rational number. Hence root 2 is irrational number. Prove that root 2 is an irrational number. If possible, let root 3 be a rational number and let its simplest form a upon b. Then a and b an integer having no common factor other than 1, and b is not equal to 0. Now root 2 is equal to a upon b. On squaring, root 3 is equal to a upon b whole square. Then 3 is equal to a square upon b square. A square is equal to 3b square. It is 1. Equation number 1. Here it's proved that 3 divides a square. It means 3 also divides a. Let a is equal to 3c for some integer c. Putting a is equal to 3c in equation number 1, we get 3b square is equal to 9c square. Then b square is equal to 3c square. It is only done when we are letting again. 3 divides b square, 3 divides also b. Thus 3 is a common factor of a and b. But this contradicts the fact that a and b have no common factor other than 1. The contradiction arises by assuming that root 2 is a rational number. Hence root 3 is an irrational number. Classify the following number as a rational number. As a rational number, 22 upon 7 is a rational number because it is in the form of p upon q. That is why it is rational number. 3.1416 is a rational number because it is a terminating decimal. Pi is a rational number. 3.142857, the bar is overhead, means it is repetitive, it is non-terminating and reoccurring. So it is rational number. .636363 is repeating. We use this sign for it. So that is this rational number. It is non-terminating and reoccurring. 2.04, 004, 0004 means nothing is completely divisible, nothing is reoccurring, so that it is irrational. Non-terminating, non-reoccurring. It is a 1.535335333. It is a rational number. Why? Because it is non-terminating and non-reoccurring. Non-terminating 3.12122 is a rational. Non-terminating, non-reoccurring. Root 21 is equal to root 3 and root 7. Root 3 is a rational number, root 7 is a rational number. We know that by the type second. So that it is irrational. Cube root of 3 is also irrational. If a A rational number find between root 2 and root 3. We do that. Root 2 is 1.414, root 3 is 1.732. So that here we write 2, not 1. 1.5152 and 1.61. We do this. If a rational number and root 2 is a rational number, then prove that a plus root b is irrational. Let a be rational and root b is irrational. Then we have to prove that a plus root b is a rational number. If possible, let a plus root b is a rational number, then a plus root b is rational and a rational number a plus root b minus a is a rational number. A and a cancelled, so that root b is rational number. But we know that this is the contradiction. The fact is root b is irrational. The contradiction arises by assuming that a plus root b is a rational number, hence a plus root b is an irrational number. These are the lines which always you should learn like. Otherwise you will be getting the problems. Example, prove that 5 plus 3 root 2 is irrational, it being given that root 2 is irrational. If the possible, let 5 plus 3 root 2 be rational. Its simplest form be a upon b, where a and b are integer and b is not equal to. Then 5 plus 3 root 2 a upon b. 3 root 2 is equal to a upon b minus 5. Root 2 is equal to 1 upon 3 a upon b minus 5. Root 2 is equal to 1 a upon 3b minus 5 upon 3. It is equation number 1. Now, a upon b is rational, a upon 3b is irrational, a upon 3b minus 5 by 3 is irrational, root 2 is rational, but it is given that root 2 is irrational. Thus we arrive as a contradiction. Since the contradiction arises by assuming that 5 plus 3 root 2 is a rational number, hence 5 plus 3 root 2 is a irrational number. यही भूल जाते हैं. Prove that root p plus root q is a rational number, where p and q are prime numbers. Solution. Let us assume that root p plus root q rational number. First we think we have to take the wrong step, that rational, and then prove it is irrational. Then there exist co-primes a and b, means they have the common factors. Root p plus root q is equal to a upon b. Then we take root p is equal to a upon b minus root q. Taking square of it, root p a upon b minus q square, it is p is equal to a square upon b square plus q minus 2a upon b root q. 2a upon b root q is equal to a square upon b square plus q minus p. Root q is equal to b upon 2a square upon b square plus q minus p. Since a, b, p, q integers, so it is a rational number. Thus root q is also a rational number. But we know that q being prime, root q is irrational. So we arrive at a contradiction. Since the contradiction arises by assuming that root p plus root q is rational number, hence root p plus root q is irrational number. Thank you for watching my channel.